My fondest memory. Oh, it's usually when I discover something that I think nobody has seen before. But that happens very rarely because most of the things you think of, somebody else has done before.
This episode is sponsored by Numerai. Are you a data scientist looking to make a real world impact with your skills? Do you love competing against the best minds in the world? Well, introducing Numerai, the revolutionary cutting edge AI driven hedge fund that's changing the game for good. Numerai combines a competitive data science tournament with powerful, clean stock market data, enabling you to predict the market like never before. Sign up now, become part of the elite community, taking the stock market by storm, and I'll see you on the leaderboard. Wonderful. So today is a momentous occasion. What an episode of MLST we're going to have. We're joined not by a godfather of AI, but the father of AI, Jürgen Schmidhuber, the researcher responsible for leading the research groups which invented much of the technology which has powered the deep learning revolution. It's long been a dream to get you on the podcast, Jürgen. It feels like the day has finally arrived. So welcome to MLST.
Thank you, Tim, for these very kind words and this very generous introduction.
So on that, let's discuss the credit assignment problem in machine learning. Now, you've dedicated a significant amount of time researching and publishing the actual history of the field. And there's a significant divergence between the public narrative and what actually happened. And amazingly, no one has pointed out any factual inaccuracies in your accounts, but the incorrect perceptions still persevere. Now, I particularly enjoyed reading your history of the breakthroughs in machine learning, going back to ancient times and, of course, even remarking on the very first computer scientist, Leibniz. And for example, you pointed out the history of who invented backprop and the CNN. And you explained that there wasn't really a neural network winter at all in the 1970s. So could you just sketch out a little bit of that history?
So that's challenge. Actually, computer science history and computing history started maybe 2,000 years ago when Heron of Alexandria built the first program-controlled machine. That was 2,000 years ago, in the first century, basically. And he basically built an automaton that was programmed through a cable, which was wrapped around a rotating cylinder, which had certain knobs, and then there was a weight which pulled it down, and the whole apparatus was able to direct the movements of little robots, of little puppets in an automatic theater. That, as far as I know, was the first program-controlled machine in the history of mankind. Even before that, there were other machines. The ancient Greeks had even earlier the Antikythera mechanism, which was kind of a clock, an astronomical clock. But then more recently, we have seen many additional advances. And you mentioned Leibniz, of course, who is of special interest to our field because he not only is called the first computer scientist, because he had the first machine with a memory, and that was in the 1680s, I think. He not only had the first machine that could do all the basic arithmetic operations, which are addition, multiplication, division, and subtraction. Then he not only had these first ideas for a universal problem solver that would solve all kinds of questions, even philosophical questions, just through computation. And he not only was the first who had this algebra of thought, which is deductively equivalent to the much later Boolean algebra. So in many ways he was a pioneer, but especially in our field in deep learning, he contributed something essential, which is really central for this field, which is the chain rule. I think 1676, that's when he published that, and that's what is now being trained to, what is now being used to train very deep artificial neural networks, and also shallow neural networks and recurrent neural networks. And everything that we are using in modern AI is really, in many ways, depending on that early work. But then, of course, there was so much additional work. The first neural networks, as we know them, they came up about around 1800. That's when Gauss and Legendre had the linear neural networks, the linear perceptrons, in the sense that they were linear without being without having any non-differential aspect to it. These first neural networks back then were called method of least squares, and the training method was regression, and the error function was exactly the same that we use today. And it was basically just a network with a set of inputs and a set of outputs and a linear mapping from the inputs to the outputs, and you could learn to adjust the weights of these connections. So that was the first linear neural network, and many additional later developments led to what we have today.
You had this beautiful statement. You said that machine learning is the science of credit assignment, and we should apply that same science to the field itself. And I guess what I'm really curious about is, first, if you could educate our listeners just a bit on what credit assignment is in the context of, say, machine learning, and why you think it's important that should apply to the field in general. Why should we care about credit assignment? Why should we study the history of the developments in the field? Why is it important?
I'm interested in credit assignment, not only in machine learning, but also in the history of machine learning, because machine learning itself is the science of credit assignment. What does that mean? Suppose you have a complicated machine which is influencing the world in a way that leads to the solution of a problem, and maybe the machine solves the problem. But then the big question is, which of the components, of these many components, were responsible? Some of them were active a long time ago and others later, and early actions set the stage for later actions. Now, if you want to improve the performance of the machine, you should figure out how the components contribute to the overall success. And this is what credit assignment is about. And in machine learning in general, we have a system consisting of lots of many machine learning engineers and mathematicians and hardware builders and all kinds of people. And there you also would like to figure out which parts of the system are responsible for later successes.
Yeah, and it's a brilliant point, and I completely agree with you, by the way. And I think the way I think about it is, you've got this giant architecture of humanity, and in it are these certain nodes. It may be an individual, it may be a research group, and if they come up with things that are very helpful, right, you want to try and direct more attention, more resources, at that nodule, at that node, right, because it's likely to come up with additional very, very important things. And if we don't get that right, we're just not optimizing the algorithm of science as a whole.
That's right, yes. Machine learning and science in general is based on this principle of credit assignment, where credit usually doesn't come in form of money, sometimes also in form of money, but in form of reputation. And then the whole system is set up such that you create an incentive for people who have worked on improving some method to to credit those who maybe came up with the original method, and to just have these chains of credit assignment that make clear who did what when, because the whole system is based on this incentive. And yes, those who are then credited with certain valuable contributions, they also can get reasonable jobs and within the economy and so on. But that's more like the secondary consequence of the basic principle. And that's why all PhD advisors teach their PhD students to be meticulous when it comes to credit assignment to past work.
So one last question, if I may. I've really enjoyed studying the history of advancement because I found that when I go back and read original source materials, let's say Einstein's first paper on diffusion, okay, or anything like that, because they're breaking new ground, they're kind of considering like a wider array of possibilities. And then over time, the field becomes more and more focused kind of on a narrower avenue of that. And you can go back and look at the original work and actually gain a lot of inspiration for alternative approaches or alternative considerations. So in a sense, it's kind of in the sense of forgetting is as important as learning. Sometimes we need to go back to go down a different branch of the tree, if you will, and expand the breadth of the search a little bit. I'm curious if you've noticed that same phenomenon.
Yes, science in general is about failure, and 99% of all scientific activity is about creating failures. But then you learn from these failures, and you do backtracking, and you go back to a previous decision point where you maybe made the wrong decision and pursued the wrong avenue, but now you have a branching point and you pursue an alternative. And in a field that is rapidly moving forward, you don't go back very far, usually. You just go back to a recent paper which came out 5 months ago, and maybe you have a little improvement there. And then maybe there's yet another little improvement there. And some parts of our field are at the moment a little bit like that, where PhD students are moving in, who just look at the most recent papers and then find a way of improving it a little bit, and 2% better results on this particular benchmark. And then the same guys are also reviewing at major conferences papers by similar students and so on. And so then sometimes what happens is that no very deep backtracking is happening, just because the actors aren't really aware of the entire search tree that has already been explored in the past. On the other hand, science has this way of healing itself, and since you can gain reputation by identifying maybe more relevant points, branching points, you have this incentive within the whole system to improve things as much as you can, sometimes by going back much further.
So there's been a lot of discussion in the discourse around this concept of AI existential risk. And you've published quite a few pieces about this recently, prominently in The Guardian and in Forbes, actually. And one of the things I wanted to focus on is this concept of recursive self-improvement, because that seems to be one of the plausible explanations that these folks give. And of course, when it comes to recursive self-improvement, you are an expert in this field. I mean, Gödel machines come to mind immediately. So I want to kind of explore asymptotes and limitations.
This whole idea of recursive self-improvement is very sexy, isn't it? In fact, it is the one idea that motivated me to do all of this. So my first paper ever in 1987, that was my diploma thesis, and it was about this recursive self-improvement thing. So it was about a machine that learns something in a domain, but not only that, it also learns on top of that to learn a better learning algorithm based on experience in the lower level domains, and then also recursively learns to improve the way it learns, and then also recursively learns to improve the way it improves the way it learns. And yeah, I call that meta learning. And back then, I had this hierarchy with, in principle, infinite self improvement in the recursive way. Although it is always limited by the limited time that you run the system like that. And then, of course, the motivation behind that is that you don't want to have an artificial system that is stuck always with the same old human-designed learning algorithm. No, you want something that improves that learning algorithm without any limitations, except for the limitations of physics and computability. And so much of what I have been doing since then is really about that. Self-improvement in different settings, where you have, on the one hand, reinforcement learning systems that learn in an environment to better interact and better create ways of learning from these interactions to learn faster and to learn to improve the way of learning faster, and so on. And then also gradient-based systems, artificial neural networks that learn through gradient descent, which is a pre-wired, human-designed learning algorithm, to come up with a better learning algorithm that works better in a given set of environments than the original human-designed one. And yeah, that started around 1992. Neural networks that learn to run their own learning algorithms on the recurrent network themselves. So you have a network which has standard connections and input units and output units, but then you have these special output units which are used to address connections within the system, within this recurrent network, and they can read and write them. And suddenly, because it's a recurrent network and therefore it is a general purpose computer, suddenly you can run arbitrary algorithms on this recurrent network, including arbitrary learning algorithms that translate incoming signals, not only the input signals, but also the evaluation signals like reinforcement signals or error signals, into weight changes, fast weight changes, where the weight changes are not dictated any longer through this gradient descent method, but no, now the network itself is learning to do that. But the initial weight matrix is still learned through gradient descent, which is propagating through all these self-referential dynamics in a way that improves the learning algorithm running on the network itself. That was 1992, and back then compute was really, really slow. It was 1,000,000 times more expensive than today, and you couldn't do much with it. But now, in recent works, all of that is working out really nicely, and it has become popular. And we have, just if you look at the past few years, a whole series of papers just on that.
So that's the fast weight programming that you're referring to?
Yes.
Yeah.
Yeah, so it's fast weight programmers that where you have a part of the network that learns to quickly reprogram another part of the network. Or the original version of that was actually two networks. So one is a slow network, and then there's another one, a fast network. And the slow network learns to generate weight changes for the second network. And the program of the second network are its weights. So the weight matrix of the second network, that is the program of the second network. And the first one, what does it do? It generates outputs. It learns to generate outputs that cause weight changes in the second network. And these weight changes are being applied to patterns, to input patterns, to queries, for example. And then the first network essentially learns to program the second network, and essentially the first network has a learning algorithm for the second network. And the first system of that kind, 1991, that was really based on keys and values. So the first network learns to program the second network by giving it keys and values, and it says, now second network, take this key and this value and associate both of them through an outer product, which just means that those units that are strongly active, they get connected through stronger connections. And the mathematical way of describing that is the outer product between key and value. So that's how the first network could program the second network. And the important thing was that the first network had to invent good keys and good values depending on the context of the input stream coming in. So it used the context to generate what is today called an attention mapping, which is then being applied to queries. And this was a first step right before the most general next step, which is then really about learning a learning algorithm running on the network itself for the weights of the network itself.
Could I press you a tiny bit on this concept of meta-learning and convergence and asymptotes? Now, one of the reasons I think why the XRisk people believe that it will just go on forever is they believe in this idea of a pure intelligence, one that doesn't have physical limitations in the real world. And I'm quite amenable to this ecological idea of intelligence, that it does, the world is a computer basically, as well as the actual brain that we're building. So surely it must hit some kind of asymptote. Do you have any intuition on what those limitations would be?
So you are talking about the ongoing acceleration of computing power and limitations thereof. Is that what you have in mind here?
Well, that's one part of it. So even if you just scale transformers, I think there would be some kind of asymptote. But we're talking here about meta-learning, learning to learn how to learn, and recursive self-improvement. And it's similar to this idea of reflection, self-reflection in language models. It actually improves the performance with successive steps of reflection, and then it levels off. It reaches an asymptote. I just believe that there are asymptotes everywhere. And that's the reason why I don't think recursive self-improvement will go on forever. But I just wondered if you had any intuitions on what those pressures are.
You are totally right. There are certain algorithms that we have discovered in past decades, which are already optimal in a way, such that you cannot really improve them any further. And no self-improvement and no fancy machine will ever be able to further improve them. There are certainly certain sorting algorithms that, under given limitations, are optimal, and you can further improve them. Well, that's one of the limits. Then, of course, there are the fundamental limitations of what's computable, first identified by Kurt Gödel in 1931. He just showed that there are certain things that no computational process can ever achieve. No computational theorem prover can prove or disprove certain theorems in a language, in a symbolic language that is powerful enough to encode certain simple principles of arithmetics and stuff like that. And so what he showed was that there are fundamental limitations to all of computation, and therefore there are fundamental limitations to any AI based on computation. And then, of course,
I'm glad you brought that topic up, because it's one of our favorite things to discuss, which is, do you think the human mind ultimately reduces to just an effective computation and so is subject to those same limits, or do you think there's any known or unknown physics that give us some out in which the brain can do a computation that amounts to hypercomputation?
Yeah. Since we have no evidence that the brain can compute something that is not computable in the traditional sense, in Gödel's sense and Turing's and Church's sense and everybody who has worked on this field, since we have no evidence, we shouldn't assume that's the case. As soon as someone shows that people can compute certain things or prove certain theorems that machines cannot prove given the same initial conditions, we should look more closely. But, there are many things that might be possible in fairy tales, and we are not really exploring them because the probability of coming up with interesting results is so low.
Fair enough. So I interrupted there. So you mentioned so far two asymptotes, one being of the mathematical kind, where there's just mathematical proofs that certain things are optimal. The other one being the limits of computation itself. What other asymptotes do you see applying to or putting bounds on recursive self-improvement?
The most obvious thing is probably light speed, and the limits.
Locality.
Physical computation, yes. And we know those. For several decades, we have happily enjoyed the fact that every 5 years, compute is getting 10 times cheaper. And this process started long before Moore's law was defined in the 60s, I believe, because even in 1941 already, when Zuse built the first program-controlled computer, this law apparently was active. So back then he could compute maybe 1 instruction per second, and since then, every 10 years a factor of 100, every 30 years a factor of 1,000,000, more or less until today. And there's no reason to believe it won't hold for a couple of additional decades, because the physical limits are much further out. The physical limits that we know are the Bremermann limit, discovered, I think, in 1983 by Bremermann. And they basically say that 1 kilogram of matter cannot compute more than 10 to the 51 instructions per second. So that's a lot of compute, but it's limited. To give you an idea of how much compute that is, I also have a kilogram of computer in here, and probably it cannot compute 10 to the 20 instructions per second. Otherwise, my head would explode because of the heat problem. But maybe it can compute something that is not so far from 10 to the 20 instructions, maybe 10 to the 17, something like that. Although most of my neurons are not active as we speak, because again, otherwise my head would just evaporate. Now, if you have an upper limit of 10 to the 20 instructions per brain, then the upper limit of all of humankind would be 10 billion times that individual limit, and that would be 10 to the 30 instructions per second. And you see, it's still far away from the 10 to the 51 instructions per second that, in principle, 1 kilogram of matter could compute. And now we have more than 10 to the 30 kilograms of matter in the solar system, and there's some. So if the current trend continues, at some point much of that is going to be used for computation, but then it will have to slow down even if the exponential acceleration will still be with us for a couple of decades, because at some point it is going to be polynomial law, because due to the limits of light speed, at some point it will be harder and harder to acquire additional mass. Once you have reached the limits of physical computation per kilogram, the only way to expand is to go outwards and, find additional stars and additional matter further away from the solar system. And there you will get a polynomial acceleration, or a polynomial growth at best. So it will be much worse than the current exponential growth that we are still enjoying.
Sure, but I would say, the existential threat, that's more than sufficient to supply an existential threat. And let me just put this a little bit differently, which is, and I agree with you on this, which is you're quoted as saying that traditional humans won't play a significant role in spreading intelligence across the universe. And I think you're right. I think we kind of share a vision of something like the von Neumann probes that go out into space and, form this, star-spanning civilization of machines and artificial intelligence that have transcended, biological limitations. So I guess my question to you is, once that spacefaring, star-spanning, civilization exists, if it becomes misaligned with us and decides that we're in the way, right? Isn't that an existential threat? I mean, might they just, repurpose the Earth, regardless of whether we're here or not, for their own aims?
Yeah, I'm often getting these questions, and there is no proof that we will be safe forever or something like that. On the other hand, it's also very clear, as far as I can judge, that all of this cannot be stopped. And it can be channeled in a very natural and, I think, good way, in a way that is good for humankind. Now, first of all, at the moment, we have a tremendous bias towards good AI. Meaning AI that is good for humans. Why? Because there is this intense commercial pressure to create stuff that humans want to buy. And they like to buy only stuff they think is good for them, which means that all the companies that are trying to devise AI products, they are maximally incentivized to generate AI products that are good for those guys who are buying them, or at least where the customers think it's good for them. So it is true, 95%. So maybe 5% of all AI research is really about AI weapons, and one has to be worried about that. One always has to be worried about weapons research, but there's a tremendous bias towards good AI. So that is one of the reasons why you can be a little bit optimistic for the future. I'm always trying to point out the two types of AIs. There are those who are just tools of users, human users, and the others that invent their own goals and they pursue their own goals. And both of them we have had for a long time. Now, for the AI tools, it's kind of clear. There's a human, and a human wants to achieve something, and so he uses or she uses that tool to achieve certain ends. And most of those are of the type, let's improve healthcare, and let's facilitate translation from one person to another one in another nation, and just make life easier and make human lives longer and healthier. Okay, so that's the AI tools. But then there are the other AIs, which also have existed in my lab for at least 32 years, which invent their own goals. And they are a little bit like little scientists, where you have an incentive to explore the environment through actions, through experiments, self-invented experiments that tell you more about how the world works, such that you can become a better and more general problem solver in that world. And so these AIs, they have for a long time created their own goals. And now, of course, the interesting question is, these more interesting AIs, what are they going to do once they are once they have been scaled up and can compete or maybe outperform humans in everything they want to achieve? So on the one hand, the AI tools, and there the greatest worry is, what are the other humans going to do to me with their AI tools? So in the extreme case, you have people who are using AI weapons against you. And maybe your neighbor has bought a little drone for $300, and it has face recognition, and it has a little gripper, and it flies across the hedge and puts some poison into your coffee or something like that. So then the problem is not the AI, which is trying to enslave humans or something silly like that. No, it's your neighbor or the other human. And generally speaking, you have to be much more afraid of other humans than you have to be of AIs, even those who define or set themselves their own goals, because you must mostly worry about those with whom you share goals. So if you share goals, then suddenly there's a potential of conflict, because maybe there's only one schnitzel over there and two persons want to eat the schnitzel, and suddenly they have a reason to fight against each other. Generally speaking, if you share goals, then you can do two things. You can either collaborate or compete. An extreme form of collaboration would be to maybe marry another person and set up a family and master life together. And an extreme form of competition would be war. And those who share goals, they have many more incentives to interact than those who don't share goals. And so humans are mostly interested in other humans because they share similar goals and because they give them reason to collaborate or to compete. Most CEOs of certain companies are interested in other CEOs of competing companies, and 5-year-old girls are mostly interested in other 5-year-old girls. And the super smart AIs of the future, who set themselves their own goals, they will be mostly interested in other super smart AIs of the future who set themselves their own goals. Generally speaking, there is not so much competition. And there are not so many shared goals between biological beings, such as humans, and a new type of life that, as you mentioned, can expand into the universe and can multiply in a way that is completely infeasible for biological beings. So there's a certain long-term protection, at least, through lack of interest on the other side.
Okay, brilliant. There's a few things I wanted to touch on there. We will get on to what it means for goals to emerge from systems later. And you started off by saying that humans will buy products that make them feel good. And Facebook is quite an interesting example to play with, actually, because Facebook is a little bit like an AI system, which is a collective intelligence. And humans use Facebook, but they have some idea that it might cause them harm. And the thing with population ethics is we know that our moral reasoning kind of decays over space and even more so over time. And part of the reason why time is so difficult is because it's predictive. We don't actually know what's going to happen in the future. So our kind of reasoning about establishing what the value of something is very, very faulty. And I think that's one of the reasons why these people would say that we don't really know what's good for us. I do completely agree with you, though, that the problem, I think, is humans rather than AIs on their own.
Yes, these are good points.
Feel free to offer some thoughts.
Yes, I mean, it would, that's a whole separate discussion, isn't it? When you discuss the limitations of what's predictable and how people often fail to see what's good for them.
Well, I think maybe. So you've already said that there's no proof that we'll be safe forever, right? Like, I mean, there could come an existential risk, from AI. So I think my question to you is, do you have sympathy for the folks who say we need to be putting more resources into researching alignment? Like, we need to develop the tools in order to allow it to be easier for people to construct AI that is aligned for the goals, and to make sure that that it doesn't have unintended consequences. Like, in other words, there may not be a proof that we can go forever and be safe for AI, but we at least want to develop the basic mechanics that we need to safely develop and deploy AI, don't we?
Yes, I sympathize with those who are devoting their lives to alignment issues and trying to build AIs aligned with humans. I view them as part of the evolution of all kinds of other ideas that come up as not only nations compete with other nations, but companies compete with other companies, and shareholders of different companies compete with shareholders of different companies, and so on. And so there is such a huge set of different human goals which are not aligned with each other that makes me doubt that you will come up with a general system that all humans can accept, simply because if you put 10 humans in a room and ask them what is good, they will give you 10 different opinions. However, I sympathize with this goal, and it's good that people are worried and they spend resources on solving some of these issues. In the long run, however, I think there is no way of stopping all kinds of AIs from having all kinds of goals that have very little to do with humans. The universe itself is built in a certain way that apparently derives it from very simple initial conditions to more and more complexity. And now we have reached a certain stage after 13.8 billion years of evolution, and it seems clear that this cannot be the end of it, because the universe is still young. It's going to be much older than it is now. Now, there is this drive, built-in drive, of the cosmos to become more complex, and it seems clear that a civilization like ours, is a stepping stone towards something that is more complex. And
could I touch on a couple of things here? The bootloader example is kind of where I want to go with this. So a lot of the ideas of this movement can be traced back to Derek Parfit, who is a philosopher. He was a moral realist, so he thought there was such a thing as a moral fact. And I'm a bit of a relativist myself. And actually, if you trace this tree of complexity and how humans evolve over time. We might just be a stepping stone to a kind of rich, diverse, transhumanist future where we become the thing over time that we're so scared of. And I think the lens that we're using here about what's right and what's wrong is kind of, like I was saying before, it's a snapshot of humanity now. And we kind of think of it as just this monolithic single thing. So does it really work when you project out to how we're going to evolve in the future?
Well, first of all, humankind is not a monolithic thing. So many of these arguments go like, we should not do that because of that. We should not do that because of that. But there is no us, there is no we. There are only almost 10 billion different people, and they all have different ideas about what's good for them. And so for thousands of years, we had these evolutions of ideas and of devices and of philosophies partially competing and partially compatible with each other, which in the end led to the current values that some people agree with, and other people over there, they agree with different values. Nevertheless, there are certain values that have become more popular than others, more successful, more evolutionary, with more success during the evolution of ideas. And so, given this entire context of evolution of concepts and accepted ideas of what should be done or what is worth being supported and what's not worth being supported, all of this has changed a lot. If we look back 200 years, the average people in the West had different ideas of what's good than today. And this evolution of ideas is not going to stop anytime soon.
Just a final question on this. There is a very real existential risk right now of nuclear Armageddon. A real risk right now. And if I were a rational person, I would be devoting all of my effort into that and other risks associated. So do you think it's a little bit weird that so much focus is on this AI XRisk?
To me, it's indeed weird. Now there are all these letters coming out warning of the dangers of AI. And I think some of the guys who are writing these letters, they are just seeking attention because they know that AI dystopia are attracting more attention than documentaries about the benefits of AI in healthcare and stuff like that. But generally speaking, I am much more worried about nuclear bombs than about AI weapons. A nuclear bomb, a big one, can wipe out 10 million people, a big city within a few milliseconds, without any face recognition, just like that, without any AI. And so in that sense, it's much more harmful than the comparatively harmless AI weapons that we have today and that we can currently conceive of. So yes, I'm much more worried about a 60-year-old technology that can wipe out civilization within 2 hours without any AI.
Well, I guess since we're not really going to worry about AI for the moment, we can turn our attention back to discussing with you how we develop AI. So I'm really curious with just the vast breadth and depth of your knowledge over the history of AI and the state of the art. I'm curious, which current approaches you're most excited about, and or what's on the horizon that for any of our listeners out there thinking about going into AI research, machine learning research. What may be alternatives that aren't getting enough attention should they look into studying and perhaps choosing to research?
At the moment, the limelight is on language models, large language models, which pass the Turing test and do all kinds of things that seemed inconceivable just a couple of years ago, at least to some of those who are now surprised. But of course, that is just a tiny part of what's going to be important to develop true AI, AGI, artificial general intelligence. On the other hand, the roots of what we need to develop true AI also come from the previous millennium. They are not new. And of course, what you need is an environment to interact with. And you need an agent that can manipulate the environment, and you need a way of learning to improve the rewards that you get from this environment as you are interacting with it within a single lifetime. So one of the important aspects of reinforcement learning, what we are now talking about, is that you have only one single life. You don't have repeatable episodes, like in most of traditional reinforcement learning. No, you have only one single life. And in the beginning, you know nothing, and then after 30% of your life is over, you know something about life, and all you know is the data that you collected during these first 30% of your life. And now there is an infinite, almost infinite set of possibilities of futures. And from this little short experience, you have to generalize somehow and try to select action sequences that lead to the most promising futures that you can shape yourself through your actions. Now, to achieve all of that, you need to build a model of the world, a predictive model of the world, which means that you have to be able to learn over time to predict the consequences of your actions, such that you can use this model of the world that you are acquiring there to plan ahead. And you want to do that in a way that isn't a naive way, which we had in 1990, which is millisecond by millisecond planning, where you say, okay, now I'm moving from A to B, and the way to do it is first move that little pinky muscle a little bit and move it a little bit more and move it a little bit more and then get up and so on. No, you want to do that in a high level way, in a hierarchical way, in a way that allows you to focus on the important abstract concepts. For example, as you are trying to go from your home to Beijing, you decompose this whole future into a couple of sub-goals. You say a first important step is to go to the cab station and get a taxi to the airport, and then in the airport you will find your plane, and then for 9 hours nothing is going to happen, and you exit in Beijing and have to find another cab, and so on. So you don't do millisecond by millisecond detailed planning. No, you have high-level planning to just reduce the computational effort and focus on the essentials of what you want to do. So that is something that most current systems don't do, but for a long time we have had systems like that, and they are getting more sophisticated over time. Important, you have a predictive model of the world that is not just focusing on the pixels and predicting how does the video change as I'm moving my hand back and forth, the video that I get through my cameras, my eyes, and so on. No, higher level concepts that reflect islands of predictability. Many things are not predictable, but certain abstract representations of these things are predictable. And so how can you discover these higher level concepts that you need to efficiently think about your own future options and select those that are most promising in the single life?
Yeah. Yeah. This is really interesting. So we've been speaking with Carl Friston, for example, and he talks about this collective intelligence where you have this multi-agent cybernetic framework, which is causally closed. And one of the things we're talking about here really is not the model itself. People talk about ChatGPT, and it's just a model, and people have configured it in arrangements that have varying degrees of autonomy. And in the future, we will develop these collective intelligences, and they're not just predicting the actions and behaviors of other agents, but even the world that we're in is a computer to some extent. So when you imbue agents with this kind of creativity and autonomy, that's the thing that I don't think people really understand what might emerge from that. It's related to this discussion about what kind of goals might emerge from that. Do you have any intuition on what that would look like?
Yeah, let me give you just the simplest example that we had in 1990, so 32 years ago, of a system that sets itself its own goals. And it consists of 2 artificial neural networks. And I know that Carl Friston is very interested in that, and only recently, for the first time in my life, I was on a paper where he was co-author just a year ago. And so back then, it was really about a reinforcement learning agent, and it interacts with the world, and it generates actions that change the world. And then there is another network which just is trying to predict the consequences of the actions in the environment. So the reactions of the environment to these actions. And so that becomes a world model. And then what kind of goal was there which was different from traditional goals? Well, in the beginning, this model of the world, this prediction machine, which is a model of the world, a world model, knows nothing. So it has high error as it is trying to predict the next thing, as it is trying to predict the reactions of the environment to the actions of the agent. So as this second network is trying to reduce its prediction error through gradient descent, through backpropagation essentially, the other one is trying to generate actions, outputs, that maximize the same error. So basically, the goal, the self-invented goal, if you will, of the first network is to generate an action whose consequences cannot yet be predicted by the other network, by the model of the world. So the first network is generating outputs that surprise the second network. So suddenly you have an incentive where the first network is trying to invent actions, experiments that fool or that surprise the second network. And that was called artificial curiosity. So now suddenly you have a little agent which, a little bit like a baby, doesn't learn by imitating the parents. No, it learns by inventing its own little sub-goals, and it's trying to surprise itself and have fun by playing with the toys and observing new unpredictable things, which, however, become predictable over time and therefore become boring. And then it has another incentive to invent additional experiments such that it still can surprise its model of the world, which in turn is improving, and so on. So artificial curiosity.
Does that also have the effect of making the network, which is trying to predict, does it have the effect of making it more robust and more generalizable, like almost a form of, regularization kind of built in this pairing?
Yeah, you can build into that network all kinds of regularizers, an orthogonal concept, which is also very important. So that was just the first version. That was really in 1990. And then we had a long string of papers just on improvements of this original concept of artificial curiosity. So this old system is basically what you now know as GANs, generative adversarial networks, because the first network is generating a probability distribution over outputs. And the second network is then predicting the consequences of these outputs in the environment. And if the output is an image, then the consequence can be either this image is of a certain type, yes, or not, no. And then that's all that the prediction machine, the world model, predicts in that simple case. And you minimize, the first network minimizes the same error function that the second one maximizes. So then you have basically a GAN. But then you don't have what you just mentioned yet, the regularizer. As a scientist, what you really want to learn is a model of the world that extracts the regularities in the environment, that finds predictable things which are regular in the sense that there's a short explanation thereof. For example, if you have falling objects in a video, then they all fall in the same way, they accelerate in the same way, which means it's predictable what these objects do. If you see 2 of the frames, you can predict the 3rd frame pretty well. And the law behind that is very simple. This means that you can greatly compress the video that is coming in, because you can, instead of storing all the pixels, you can compute many of these pixels by just looking at 2 successive frames and predicting the 3rd frame, or maybe 3 successive frames and predicting the 4th frame, something like that. And you only have to encode the deviations from the prediction. So everything else you don't have to store separately, which means once you understand gravity, you can greatly compress the video. So that's what you really want to do. And so the more advanced version of artificial curiosity is about that, where you have a motivation to find a description of the data which is coming in, of the video, of the falling apples, for example, that is simpler than the one that you had before. So before you had the simple explanation of the data, you needed so many bits to describe the data, and afterwards only so many. And the difference between before and after, that is the reward that you get. So that's the true reward that the controller, the first neural network, should get in response to the improvements of the second network, which are now measured in terms of compression progress. So first, I needed so many resources to encode the data, but then I discovered this regularity, gravity, and I can greatly compress all kinds of videos that are reflecting the concept of gravity, and suddenly I have a huge insight into the nature of the world, and that is my true joy, scientific as a scientist, my true joy as a scientist, that I want to encode in a little number, which is given as a reward to the guy who is inventing the experiments that lead to the data with the falling apples, for example.
Right. Well, and of course, this has been a challenge in machine learning, since the beginning, which is, okay, as we add more and more parameters, how do we prevent it from learning spurious information with those parameters and instead have it focus on parsimonious explanations, on regular explanations, on things that in this universe are more likely to generalize, to unseen examples. And so I think my question to you is, does this setup that you described, is it a form of that, and or what is the state of the art, these days for helping to push or nudge neural networks towards learning parsimonious models for the world rather than highly detailed, spurious, susceptible to, high frequency anomalies and adversarial examples and all this sort of thing?
Mm-hmm. Yes. What is the current state of the art in regularizing descriptors of the data, such as neural networks, such that you get simple explanations of the data, such that you get short programs that compute the data? In other words, such that the description of the data is a short program that computes the much larger raw data.
Precisely.
And how close can we get to the limits which are given through this concept of algorithmic information, or Kolmogorov complexity? Kolmogorov complexity of any data is the length of the shortest program on some general computer that computes it. Since in our field, the general computers are recurrent neural networks, we want to find a simple recurrent network that computes all this data. And given one computation of the data, we want to find an even simpler one. So we want to have this idea of compression progress. And here, I have to say, although we have lots of regularizers invented throughout the past few decades, there's nothing that is really convincing. I think one of the really important missing things is to make that work in a way that is truly convincing. That is as convincing as ChatGPT is today in the much more limited domain of generating text from previously observed texts and stuff. A very old idea of, I think the 1980s, was to have weight decay in a neural network, which basically is the idea that all the weights should have an incentive to become close to zero, such that you can prune them. And so people built in a regularizer that just punished weights for being large or being very negative. But that didn't work really well. And something better was flat minimum search. That was 1998. And first author, my brilliant student, Sepp Hochreiter, back then, roughly the same time when the LSTM paper came out. And there, the idea is if you have if you plot the weights of a neural network on the x-axis and you plot the error on the y-axis, then given the weights, you have high or low error, and then there is, for example, a sharp error function which has a sharp minimum, which goes like that. Can you see my finger? So here is the x-axis, here's the y-axis, here's the error, and the error for a certain weight is really, really low, but then for a different weight in the environment, in the vicinity, it's high again, which would be very different from a flat minimum, which would be like this. So here's the error, and it's going down. And for many, many weights, it is low, the error, and then it goes up again. So if you're
very sharp well versus a very broad well.
Yes, a sharp well versus a broad well. Now, if you're in a sharp well, you have to specify the weights with with high precision. So you have to spend many bits of information on encoding the weights of this network, as opposed to a flat minimum, where it doesn't matter if you perturb the weights, because the error remains low in this flat minimum. So what you really want to find is a network that has low complexity, in the sense that you can describe the good networks, those with low error, with very few bits of information. And suddenly, if you maximize or if you minimize that flat minimum second order error function, then suddenly you have a preference for networks that for example, do this. You have a hidden unit, and the outgoing weights, they have certain values, but if you give a very negative weight to the hidden unit, then it doesn't matter what all these outgoing weights do. And flat minimum search likes to find weight matrices like that, where one single weight can eliminate many others, which you suddenly don't need any longer, such that the description complexity of the whole thing is much lower than in the beginning, when you just had a random initialization of all these weights. So that is much more general than weight decay, because weight decay doesn't like these strong weights. It wants to remove them. But sometimes it's really good to have a very negative weight coming to a hidden unit, which is switched off through that weight, such that all the outgoing connections are meaningless. But it's not it's very nice. It's a very nice principle, but it's not as general as finding the shortest program on a universal computer that computes the weight matrix that is solving your problem. To the extent
how do you think we're going to get to that point? How do you think what approaches are going to lead us to finding things that approach Kolmogorov complexity?
Yeah, I think that part has again a lot to do with meta-learning, and as a system is able to run its own learning algorithm on the network itself, it can suddenly speak about the algorithms in form of weight matrices, and it can discuss concepts such as the complexity of a weight matrix, and then you can conduct a search in this space of networks that generate weight matrices, and then you suddenly are in the game. So suddenly you are playing the right game, and then it's more a question of how to choose an initial learning algorithm, such as gradient descent, to come up with something that computes the simple solutions which you really want to see in the end.
It's very interesting.
Very recent papers on that, on aspects of that, came out just a while ago with my students Vincent, Hermann, and Luis Kirsch, and Francesco Faccio, and my postdoc Kazuki Irie, and Robert Chordash also, and also Immanuel Schlag. And there the idea is really to have one network that computes an experiment. And the experiment itself is the weight matrix of a recurrent network. So there is a generator of an experiment, which can be anything that describes a computational interaction with an environment, so a program. So that experiment is then executed in the real world. There's a prediction machine that predicts the outcome of the experiment before the algorithm is executed. And so then there is just a yes or no question. Either the following outcome will occur or not. Either it will occur or not. But now the entire setup is such that you don't have predictions all the time about every single pixel. No, you just have something which is very abstract and which is just about whether a certain unit of the recurrent network is going to be on or off at the end of the experiment. And this internal on and off unit can represent any computational question, any question that you can ask at all. And now the task of the experiment generator, which is another network, which generates a recurrent network weight matrix, which represents the experiment. The task of this experiment generator is to, again, come up with something that surprises the prediction machine, which looks at the experiment and says, yeah, it's going to work or not. And suddenly you are again in this old game, except that now you have this world of abstractions where the abstractions can be anything that is computable.
Interesting.
Really cool, really cool. Could we spend the last 10 minutes or so just talking about some of the current AI landscape? So in particular, the capabilities of GPT-4, the moat building thing and the power that companies like Google and OpenAI have, and also the potential for open source. So maybe we'll just start with the very current capabilities of GPT-4. Are you impressed with it? What do you think?
I'm impressed in the sense that I like the outcomes that you get there, and it wasn't obvious a couple of years ago that it would become so good. On the other hand, of course, it's not yet this full AGI thing, and it is not really close to justifying those fears that some researchers sometimes now document in letters and public letters and so on. So to me, it's a little bit like a déjà vu, because for for many decades, I have had discussions like that, and people said, "You are crazy," when I said that within my lifetime I want to build something that is smarter than myself. And now suddenly in recent years, some of the guys who said, it's never going to happen, suddenly they just look at ChatGPT and they think, oh, now we are really close to AGI and whatever. So I don't share these extreme I'm less impressed than some of those guys, let me say that.
Right.
The open source movement that you mentioned, you want to ask a specific question about that, right?
Well, yeah, there was that famous Google memo that got leaked. And when the Waits for Llama from Facebook went out, within about 2 or 3 weeks, it was avowing pretty similar to ChatGPT, with this LoRa fine-tuning. And the open source community has just exploded. You can now run it on your laptop. And there is some question whether there is a significant gap between the capability. Is it just a parlor trick? Is it really as good potentially, or could it be as good as some of the next best models from OpenAI? But I guess the question is, do you think that we need OpenAI to have the best models?
No, of course not. No, I'm very convinced of the open source movement and have supported that. Some people say the open source movement is maybe 6 or 8 months behind the large companies that are now coming out with these models. And I think the best way of making sure that there won't be dominance through some large company is to support the open source movement. Because how can a large company compete against all these brilliant PhD students around the world who are so motivated to, within a few days, create something that is a little bit better than what the last guy has put out there on GitHub and whatever. So I'm very convinced that this open source movement is going to make sure that there won't be a huge moat for a long time.
I'm reading between the lines here, but I would guess you would be opposed to legislation like the EU is considering, where the very tight restrictions on generative models, onerous kind of approval processes and things like that, because that's going to have this chilling effect on open source innovation and the little guys, wouldn't it?
Yes, I have signed letters which support the open source movement, and whenever I get a chance to maybe influence some EU politicians, then I'm trying to contribute to making sure that they don't shoot themselves in the foot by killing innovation through the open source movement. So you certainly want to avoid that. There are lots of different open source movements around the world. So if one big entity fails to support open source, or even makes it harder for open source, there will still be lots of other entities which won't follow. And so no matter what's going to happen on the political level, I think open source is not going away.
I guess just in closing, you've been in this game for decades now, and I know it's a bit of a strange question to ask, but what's your fondest memory in your career?
My fondest memory? Oh, it's usually when I discover something that I think nobody has seen before. But that happens very rarely, because most of the things you think of, somebody else has done before. But yeah, so... Yeah, what usually happens is and this has happened many times, not many times, but quite a few times in my career since the 80s as a scientist who publishes stuff. suddenly you think, oh, that is the solution to all these problems. And now I really figured out a way of building this universal system which learns how to improve itself and learns the way to improve the way it improves itself and so on. And now we are done. And now all that's necessary is to scale it up, and it's going to solve everything. And then you think a little bit long about it, and maybe you have a couple of publications, but then it turns out something is missing. Something important is missing. And actually, it's not that great. And actually, you have to think hard to add something important to it, which then for a brief moment looks like the greatest thing since sliced bread. And then you get excited again. But then suddenly you realize, oh, it's still not finished. Something important is missing. And so it goes back and forth like that. I think that's the life of a scientist. The greatest joys are those moments where you have an insight, where suddenly things fall into place such that along the lines of what we discussed before, the description length of some solution to a problem suddenly shrinks because two puzzle pieces, they suddenly match and become one, or become one in the sense that they fit each other, such that suddenly you have the shared line between the two puzzle pieces. One is negative and the other one is positive, and suddenly the whole thing is much more compressible than the sum of the things separately. So these things, that's what's driving scientists like myself, I guess.
Wonderful. Professor Jürgen Schmidhuber, it's been an absolute honor. Thank you so much for coming on the show today. I really
Thank you. It was such a pleasure talking to you.